Hi guys, it's Miss Francis. Today we are going to start talking about lipids. Lipids are our fats, our waxes, our oils, and our steroids, where their primary functions include energy storage, structure insulation, and some hormones are lipid-based. The unifying feature of lipids is that they are hydrophobic. And this is because they have non-polar covalent bonds. There is one exception to this rule, and that includes phospholipids, which we will discuss at a later time. Lipids have carbon, hydrogen, and oxygen, but they have a hydrogen to oxygen ratio much greater than 2:1. So there's going to be many more hydrogens than oxygens. Fats are an example of lipids, and fats are composed of 1 glycerol and 3 fatty acids. The 1 glycerol and the 3 fatty acids combine via dehydration synthesis to form a fat and 3 water molecules. And these fats are going to store large amounts of energy, and they're going to insulate, cushion, and protect our organs. So fats aren't actually considered polymers because polymers are made up of repeating monomers, and fats are actually made up of glycerol and 3 fatty acids. Therefore, fats don't fit the description or the definition for a polymer. So let's get into what a fatty acid is made up. So a fatty acid is made up of a fat is made up of glycerol and 3 fatty acids. So let's tackle glycerol first. Glycerol is an alcohol that has a 3-carbon skeleton. Each carbon has its own hydroxyl group, and the way to remember it is to think of Santa Claus, who says ho, 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 and you can see you've got your 3 hydroxyl groups connected to your 3-carbon skeleton. A fatty acid also consists of a carboxyl group, which is your C double bond O OH, which is then attached to my long skeleton of carbon, often 16 to 18 carbons long. And the question asks, where do the H and the OH come from for forming water during dehydration synthesis? Well, the H comes from a hydroxyl group on glycerol, and the hydroxyl group comes from our carboxyl group on the end of our fatty acid. So let's talk a little bit more about a carboxyl group. The carboxyl group consists of a carbon atom with a double bond with an oxygen atom and a single bond to a hydroxyl group. So sometimes we pronounce it as C double bond O OH. These compounds or organic compounds that have carboxyl groups are organic acids. So fatty acids will have a carboxyl group. Amino acids will have a carboxyl group. And this carboxyl group acts as an acid because it can release its hydrogen in solution. But now when we looked at glycerol also lost a hydrogen. So why doesn't glycerol impart an acidic quality to its organic compounds? And that's because that hydrogen is going to go into the water, not into solution. So why isn't the pH of glycerol acidic? Because the H given off by glycerol isn't going into solution, it's going into a water. We mentioned this already. We said that a fat is hydrophobic due to the many nonpolar carbon-hydrogen bonds. So in order to form a fat, you need to join 3 fatty acids with a glycerol. So here's my 1, 2, 3 fatty acids, and here is my glycerol over here in gray. The links that are formed when I join my 3 fatty acids and my glycerol are called ester linkages. This is a really good video by Stephanie Castle that explores triglycerides, which is another name for fats, and the condensation reaction that forms them. Now, the 3 fatty acids within any fat can be the same or they might be different. So how can they differ? Well, they can differ in length, in other words, the number of carbons in the skeleton, and the number and the locations of double bonds. So we have saturated fatty acids and unsaturated fatty acids. Your saturated fatty acids have no carbon-to-carbon double bonds, meaning there is a hydrogen at every possible position, and that forms a straight chain, which is not good, because if I form a straight chain, there's no fluidity, there's no movement. So the saturated fatty acids build up, which can result in health issues. On the other hand, we have unsaturated fatty acids. Unsaturated fatty acids are kinked or bent because they have at least one or more carbon-carbon double bonds, and that enables the unsaturated fatty acid to have fluidity. Now, there are 2 types of unsaturated fatty acids. You've got monosaturated and polyunsaturated. So monounsaturated fatty acids have 1 double bonds between the carbons. Polyunsaturated fatty acids have more than 1 double bonds. So here's a great table that just summarizes the similarities and differences between saturated fatty acids and unsaturated fatty acids. Saturated fatty acids are all single carbon-to-carbon bonds, whereas unsaturated fatty acids have at least 1 double carbon-to-carbon bonds. Therefore, saturated fatty acids have hydrogens at every possible position on the carbon chain, whereas unsaturated fatty acids do not. When we're talking about shape, saturated fatty acids are straight versus unsaturated fatty acids, which are kinked or bent. Animals are your primary sources for saturated fats, whereas plants and fish are your primary sources for unsaturated fatty acids. Solids such as butter, margarine, and Crisco are saturated fatty acids, whereas oils, olive oil, avocado oil, grapeseed oil, are all examples of unsaturated fatty acids. You will need to know how to draw a saturated fatty acid, so we left room in your note packet in order to follow these instructions and do so. Furthermore, Stephanie Castle provides a tutorial on how to draw a saturated fatty acid. So to conclude, saturated fatty acids are solid at room temperature and make up animal fats. Usually these are the fats that are going to contribute to cardiovascular disease or heart disease, whereas your unsaturated fats contain your unsaturated fatty acids. They're liquid at room temperature, and they're found in plant and fish fats. So what's the difference between a fat and a fatty acid? Well, the fatty acids are components of a fat. And here is another video by Stephanie Castle that summarizes saturated versus monounsaturated versus polyunsaturated fatty acids. Humans have devised a way to hydrogenate oils. So what does that mean? It means to break the double bond between carbons and add a hydrogen, hence the term hydrogenation. So what does this do? Essentially, it can turn vegetable oils into solids. So it turns liquids into solids. So these food scientists, they break the double bond in the unsaturated fatty acid, and they add a hydrogen, thus unbending or unkinking that fatty acid. And now I have gone from a liquid to a solid. Another type of fatty acid is called a trans fatty acid. A trans fatty acid is when we chemically modify an unsaturated fatty acid to be structurally straight, where we have the cis configuration, which is bent, and the trans configuration, which is straight. So let's look at some more examples of cis and trans fatty acids. So a cis fatty acid has the hydrogens on the same side of the double bond, whereas the trans fatty acids have hydrogens on opposite sides. The cis molecules form more of a U, whereas the trans fatty acids are more linear. The cis fatty acids are much more common in nature. So again, unsaturated fatty acids can be cis or trans. In a cis arrangement, the hydrogen's on the same side. On the trans arrangements, one's on top, one's on bottom, where the cis fatty acid is going to be bent or kinked. A trans fatty acid is going to have a straight configuration. So like I said, most unsaturated fatty acids found in nature are in the cis configuration, but there are a small amount of naturally occurring trans fatty acids. However, many manufacturers produce the trans fatty acids by manipulating that fatty acid during the food processing. So here is a video by Stephanie Castle where she talks about the cis and trans isomers of fatty acids. Then you have some review questions that you can go through in your note packet. Here are the answers to those review questions, and tomorrow we will continue our discussion of fats.